So we ended this yesterday, but I didn't do a very good job of explaining this because I was kind of thrown off by what was going on. So I want to hit the high points of what's going on here. Peyton, please. Thank you. Okay. So this reaction, what's specifically happening? I said there was one little typo here. It was not balanced properly. But what's happening here specifically? Water's being formed. From what? Okay, it's elemental compounds, right? So in this reaction, my first question is this reaction creating more disorder or creating less disorder? How do you know it's less disorder? 3-2. Now, we'll have to look at it together because I don't remember what you're talking about. I remember the question, but I don't remember the details. Now, my next question. If they didn't even give you the reaction, but they gave you this part, could you know if it was becoming more disorder or less disorder? What is it? This is more order. Okay? So it's less disorder, more order. And either way, 6 and 1/2 a dozen the other. So it's more order. Therefore, entropy declines mainly due to blah, blah, blah. To confirm, we need to know the entropy of the surroundings. Now, here's the key word. First of all, what is entropy again? Disorder. What are the surroundings? And here's the problem. Does the surroundings mean this stuff in the green box? No. What is that? That is the system. Very good. And so that's the part that I didn't do a good job yesterday with is explaining. So here's the deal. So notice what all of these say. This says delta S of the surroundings equals Q of the surroundings over T. Remember when we did this yesterday? Remember? Okay, just to kind of throw this back at you. Remember we did the triangle, and inside the triangle we had delta S, delta H, and we had T. And so instead of saying delta H, what letter do they use? Right here. They use Q. It's the same thing. Okay. However, for this reaction, and here's the part that yesterday that I did not do a good job of. You can't really see that. This part. Delta H of the what? System. What is the sign of that value? Negative. So when this reaction happens, what type of reaction is it? How do you know that this is exo? Because it's negative. Very good. So let's look at the two things we've been talking about. Is it becoming more ordered or less ordered? More ordered, and is it endothermic or exothermic? Exo. Think about that for just a second. It's releasing energy, but it's coming together. That's a hard thing to think about. Exactly. And that's what we got to get to, because what was the question? To confirm, we need to know the entropy of the surroundings. So let's look at this. So we know this to be true. The first law of thermodynamics demands, was that say demands? Demands that this energy is, what did you say? Transferred from the, did you say that? Oh, okay, I'm sorry, I didn't hear her. So transfer from the system to the surroundings. No, the change or increase or decrease of entropy of the surroundings is the result of the energy flow into or from the surroundings as a function of temperature. So here's the two things that, again, I left off yesterday. Notice this versus this. How are delta H of the system equivalent to the delta H of the surroundings? Equal but opposite. So you just told me in the last slide that water forming is exo or endo. Exo. So the actual process of water being formed is exothermic. But that's the system. Where is it? So it's releasing energy. Well, what's there to absorb the energy? The surroundings. And so here we have release. And here we have absorb. Now, again, this is only for this particular example. This is not for all. This is just for this one. So this is where we kind of get this particular information. So that's why it's equal but opposite. But remember, the question we wanted to know was delta S of what? The surroundings. We gave you in the previous slide, one more time, delta H of the system. Well, if the system is negative, then what is delta H of the surroundings? Positive, which is exactly where, this came from. So why is it now positive 483? It's equal but opposite. So the easy question, though, is where did that 298 come from? Temperature. So look, this right here is exactly what we were just solving for. We were solving for delta S. Does that make sense? Okay, so we took this number, which was positive, what, 483? Is that right? Yes? Yes. And divided it by 298. Yes. Okay, so 0.6. Now, we've already done a problem just like this, and you did it the other day, but the one key thing that I left off yesterday was this, is that when you do the division part, you need to convert it to what unit? Joules, because S and H need to be two different things. So when you divide it, you're going to get 1,600 joules per mole over degree Kelvin. So that is going to be your delta S of the system. Go ahead. That is delta S. No, that was delta S of the surroundings. This is where we're getting to. All right. So in the very first slide, do you agree that they told you the delta S of the system was negative 88.9? Remember that? That means that water is coming together. But you just calculated the delta S of the surroundings is positive. So here's the weird part. What is the surroundings doing when that water is being formed? It's absorbing energy. And when it absorbs that energy, what is it doing? Dispersing. What does disperse mean? To spread apart, right? So disperse the crowds, right? Spray you with pepper spray. All right. So since it's dispersing, is that becoming more ordered or more disordered? More disorder. So when things are all tied together and all of a sudden they disperse, you become more disordered. So at the same time, the system is becoming more ordered, but the surroundings is becoming what? More disordered. And then here's the crazy funky part. Notice what's happening to the universe. So what is the delta S overall? Positive. So when water is formed, does the universe become more ordered or more disordered? More disordered, which doesn't make a whole lot of sense. Or does it? When water is formed, delta S is positive, right? Is that what nature wants? Is that what the universe wants? Does the universe form a whole lot of water? It's because it's very positive. Does that make sense? Nature prefers a positive delta S. The formation of water is a very high delta S. That's why nature likes making a lot of water. Okay, so the numbers prove true. Okay, so here's kind of the words. Even though the entropy of the system declines, which means, do you agree you're taking oxygen and you're putting it together to make water molecule? That's more order. The entropy change for the surroundings is so very large that the overall change for the universe is positive. So here's kind of a bottom line. A process is thermodynamically favorable. What does that mean? It's spontaneous. It'll happen on its own, in spite of a negative entropy change, as long as it's extremely exothermic. And is the process of making water exothermic? How did you know that? What was the value for the delta H of the system? Negative 483 kilojoules. That's a very large exothermic reaction. Okay? All right. In other words, sufficient exothermicity sets off system ordering. Okay? All right. Peyton, help me out. Read that first part, please.
Although the sign of delta G for physical or chemical transformation indicates the spontaneity of a change.
Pause right there. Spontaneity of a change. Now, what was the symbol that you read? Delta G. So we've kind of totally changed gears, right? Very good. Delta G naught. Spontaneity of a change. So if delta G is what sign, it's spontaneous? Negative. Okay, keep reading for me.
A little more is needed in order to relate free energy to equilibrium.
Pause right there. What two letters are we now relating? Free energy. All right, so write this in. Free energy is delta G, and what is equilibrium? K. So we're trying to talk about G and K. Do we have a formula that relates these two? What is it? Negative rat link. Okay, keep going, Peyton.
For what follows, let's consider the reaction. What is that?
A going to B. Yep. Now, here's the deal. There's two things I need to talk about. Number one, what is the entropy change in that particular reaction? 0. How do you know it's 0? Get 1 mole of a gas to 1 mole of a gas. My second question. Yes, ma'am. He's on his way? Yes. Is this reaction in going to completion or going to equilibrium? How do you know, Colby, that it's going to equilibrium? Very good. Okay. Peyton, keep reading.
Which we know is spontaneous at 298 Kelvin.
Pause. How do we know it's spontaneous? It literally just told you. So just keep that in mind. Okay, go ahead.
You have not had a significant experience with the ideas of equilibrium.
False. You do have.
Before discussing thermodynamics, it is not a shock to recognize that although the reaction happens, it does not go to completion.
Pause. Simply based on the reaction itself, how do you know it doesn't go to completion? The arrows. Okay, go ahead.
Based on discussion of K values, same as Q, but in standard conditions, as well as the entropy of mixtures as opposed to pure substances, it is no surprise that even if stoichiometric amounts of A and B react, there will still be at least a small amount of reactant in the container after equilibrium is reached.
All right, so that last part there in that blue part, even though A is going to try to convert to what? B. Once equilibrium has been achieved, will there still be some A left? Now, let me ask you this, and this is throwing it back to equilibrium. How would you know if more A or more B is present at equilibrium? So my question is, if K is greater than 1, what would you have more of, more A or more B? Why? Products are favored. What if K is less than 1? Reactants are favored. So it's one of those things like, oh yeah, I remember that now. It's just connecting all of these pieces of the puzzle. So we're going to pretend that this is spontaneous, which means what is delta G? Negative. And what is K? Greater than 1. So that's one thing that we can go back up here, and please add this. This is important. As soon as it says the word spontaneous, we know that delta G is negative and K is greater than 1. Is that true or false? If we threw E in, what would E be? It would also be positive. So my question then should make sense. If this is a spontaneous reaction, you know K is greater than 1, then is it true that B should be the most abundant species once equilibrium has been achieved? Yes, okay, as long as we're on the same page there. However, is B the only species contained at equilibrium? No. Is there a little bit of A left? Yes. Okay, so we can kind of go on. All right, so Peyton, keep reading, please, ma'am. Let's use. Okay, no.
Let's use this information for assume we have some amount of pure A and it begins to react to form B. As the reaction proceeds, what must happen to the entropy of the universe? In the figure below, 3 possible examples are given as the reaction proceeds from A to B.
All right, now, what is the question specifically? The entropy of the universe. So what letter are we looking for? S. And we're trying to determine, is the universe becoming more disorganized or is it becoming more organized? So C, if you can figure out, just think. Again, there is a right answer, and I'm going to talk about what the right answer is. But again, notice what we have. Let me kind of explain it because it's a little difficult. So we're going 100% A. What's happening as we're going this way? It's reacting, and we're making what? Pure B. Now let me ask you this. Will we stop making B at some point? Keep that in mind. It's either going to be 1, 2, or 3. Yep. Which line represents the delta S of the universe? All right. By show of hands, how many of you think it's line 1? Line 2? Line 3? Okay, so let's read the answer. Pate, would you like to read the answer again?
Sure.
That'd be fantastic.
If we consider each path, we can easily eliminate 2 of them. Since we know the reaction between A and B occurs, path 3 is not possible.
All right, pause. Before you read that, if I go back and look, why do you think path B is impossible? Well, let me ask you something. In terms of concentration, never mind. Go ahead. Let's keep reading. No, I don't want to explain that. Go ahead. All right, so, and here's the deal. We know that the entropy should be becoming more disorganized, okay? And so basically what this is saying is the entropy decreases. So, and I probably should have explained this, that the x-axis, the y-axis is delta S. Like, will you, Aaron, please? Okay, it is delta S. All right, hang on one second. All right, Peyton, go ahead. So, one more time. Path 3 is not possible because it violates the second law by allowing the entropy to decrease as the reaction proceeds. Okay, go ahead.
In addition, path 2 cannot occur either because it says that the entropy would increase without bound.
Pause right there. What does it mean without bound? That basically that the universe would no longer exist because it would just space it so far out that there would be nothing left. So that's not possible because the universe is destroyed if entropy continues to increase. Okay, go ahead.
Until the reaction mixture only contains pure B.
All right, now one other thing I want to mention about this, if you go back and look, and I asked you this, I said, will we eventually stop making B? And you said yes. Well, look at that black line. If we continue that line, where would B end? No. It is what's that word when it projects? No. No, there's a word that basically you don't know it'll come to me. Anyways, but all right, so keep reading. If this were
If this were the case, the equilibrium constant would be infinite, counted by experimental problem-solving evidence relating to chemical reactions. Thus, path 1 must give a general description of how the entropy of the universe changes with our spontaneous reaction. The reaction will proceed in the forward direction as long as the entropy of the universe increases. Once we reach that maximum, the reaction stops. More specifically, we have reached equal.
all right, so basically what happens is that, and this is what I want you to do. From this point, and matter of fact, let's actually do this because it'll be a lot prettier. You guys are probably can do it better than I can. Oh wow, that was bad. I want a straight line. So do me a favor. Draw a straight line and do this. So draw them from the origin, from where all pure A is, to where pure B ends. And this is the part that I'm referring to. Yeah, give me a second. Nice hands. Nice hands. Once you draw the straight line, like I said, make sure you get this part. So, remember when we did something called Hess's Law, right? Hess's Law is the change between products and reactants. Well, in Hess's Law, whenever we're talking about thermodiagrams, do you agree we had that little hill called activation energy? Same kind of concept here. The entropy will initially increase above the amount desired, but then what will naturally happen? It will kind of balance itself back out. So we'll make a maximum of B, but then what begins to happen to B? So right here, this part right here is equilibrium. So that is the maximum amount of B that we can make. Well, are we making 100% B? No, you told me at the very beginning, well, some A, B left. Yes, so this up here is max B. Well, then why did it then decrease? But what I'm saying, equilibrium is achieved, but then what do we know about equilibrium? That's max B. So what does B have to turn back into? A. So from this point, what is B doing? It's going from B back into A. Okay? Does that make sense? Yes. So the apex then turns back into the reverse direction. Yep, it basically, and it goes back and forth. Yep. Exactly. Say it again. Line 2? No. No. Just keep it. I don't necessarily know if that's this. I don't necessarily know how to answer that. All right. So remember, if the entropy.
Can I read?
Yeah. Go ahead.
Remember, the entropy of the universe. Wait, no. Remember, if the entropy of the universe increases, the free energy of the system decreases.
All right. So pause right there. If the entropy is increasing, is that what nature wants? Yes. If the free energy of the system is decreasing, is that what nature wants? Yes, because you're utilizing the energy to push things farther apart, to make it become more disordered. So, in essence, you have a positive delta S, right? That's what we want. And what about, well, actually, let me do this in the right colors. All right, so we have wow, that's not right either. So we have a positive delta S. So do me a favor, and I know above the word entropy, put positive. And then what's going to happen to our delta G? It's going to be negative. And those are the two signs that nature is trying to get itself to. Go ahead, Peyton, you can read the rest of it.
Since we have a general idea of how the entropy of the universe changes as the reaction proceeds, what happens to the free energy of the system during the course of the reaction? As free energy and entropy are inversely related, the graph must look something like.
All right. So tell me if you recognize this graph. So what you just told me, as the entropy, if the universe of the entropy goes up, what does delta G do? It goes down. So if you take this graph and you take a mirror image of graph 1, are they almost identical? Yes. Exactly. Is utilizing it to become more disorganized. The universe blows up. Okay. So, what I'm wanting you to see here is that the delta G is equal but opposite to the change in entropy. So what the universe is doing is using the free energy to make things become what? More disorganized. Okay? Same difference. Because remember, where does the energy come from? The system. So the delta G has to be with the system, but the entropy is of the universe.
But they're opposite. Okay, but if the free energy of the system is decreasing with the entropy of the universe.
Increase. Okay? Go ahead. Yes. Yes. Yeah. And so again, the one thing that I wanted you to notice was this aspect right here. So from here to here is really our change in free energy. Because notice at equilibrium, what does some of that A then do? It absorbs some of the energy back. Because, do you agree that so this would be releasing energy, right? So this is releasing. But what happens when B converts back to A? What happens to some of the energy? It is absorbed. Okay? Well, if it's absorbed, that's what's going on from this point. Because technically on the y-axis, what are happening to those values in that blue circle? They're becoming more positive, right? Well, what happens when delta G is positive? That's not what it's wanting to happen. But it has to maintain what? Equilibrium. Okay? So it comes to a finite point, which eventually it's got to maintain some sort of equilibrium. All right, so Peyton, you want to read that one?
As the reaction proceeds from pier A towards pier B, the free energy must lower. The reaction is consuming the free energy available to do the work, eventually reaching a minimum when the system reaches equilibrium. The question becomes, how can we use this graph to obtain experimental information about the equilibrium position?
All right, so this is going to connect G and K. So we're already kind of seeing how all of them work. So when delta G is at its minimum on this graph, do you agree that this entire graph is about delta G? When is delta G at its minimum? So when delta G has used all of the energy that can possibly use, what's happening to the reaction? It's at equilibrium. Okay? So, when we know the value of delta G, can you then relate it to K? How? So let me ask you this. Do you agree that this black slope line is delta G? So what if I wanted to know where we are in reference to equilibrium at that point? Derivative and then the double derivative and then an integral of that one. I'm totally kidding. I don't want to go that far. But here's my point of emphasis. If I know that this is the value of delta G, have I achieved equilibrium yet? So K is still less than 1. How do I know that K is still less than 1 right here? Excuse me. Check. K is greater than 1 because what way is it still wanting to proceed? It's still wanting to proceed forward, right? Well, what happens when you go beyond equilibrium? It's in the reverse. So you can know equilibrium at any point on this graph because of the value of delta G. And you can know where that relates to the point of equilibrium. So if you don't have enough free energy, can you get to equilibrium? No, because what happens if the only amount of energy that I give you is where that X is? What's going to happen? You're not going to achieve equilibrium. You can only make a certain amount because that's where equilibrium is going to. It's not going to get you to the point where you need. So does that make sense? So is it amazing that reactions even react at all? It should be, because all of this stuff is going on right now without us realizing that it's happening. All right, so to finally talk about delta G, the final summation of all of this, and the whole key is we want to know if the reaction is spontaneous or not. We can have all this entropy going back and forth, we can have all this enthalpy going back and forth, but ultimately delta G is really going to decide, because if I don't give you enough energy to do the job, you're not going to be able to do it. Okay, Devin, if I wanted you to go to run 6 miles, but I didn't give you any food for a day, could you do it? Okay, well, you're a superhuman. Most of us couldn't do it. But the point is you've got to have some sort of energy to be able to do that. Again, this is the same basic thermodynamic graph. I don't like this particular picture. The only thing that I wanted to show you were two things. Number one, first of all, what is this particular stuff reacting? Glucose and oxygen, which is what process? Cellular respiration. Glucose and oxygen. We breathe in oxygen, we give off carbon dioxide. Okay, so what type of reaction is this? Combustion. What is this hill? Activation energy. Is this exothermic or endothermic? What is the sign of the slope? It is negative, so it's exothermic. How long did it take? That's a trick question. Why? We haven't done kinetics. There's no time. Okay, so kinetics will tell us how long that it takes. All right, moving on. So have you seen that before? That's Hess's law. And I told you when we did Hess's, there was 3 versions of Hess's. Now, here's something interesting that pops back up here at the bottom. Read that very, very bottom statement, Peyton. Very bottom one.
Delta G is any element in its stable form is 0.
Have you heard that before? Who else has a 0 for stable elements? H. Can S be 0? No. Why? What's that? First of all, which law is that? That's the third law. That's the third law of thermodynamics, which tells you that there's no such thing as a perfect crystal because we don't have absolute 0. So that's what's going on there. So again, the standard free energy of formation is the free energy change that occurs when 1 mole of the compound is formed from its elements in their standard state. So that's kind of what's going on there. Negative delta G's are thermodynamically favorable. We already know that. We already know negative Enfe. We already know negative Ratlink. We already know Hess's law version 3. Again, the only difference between this one and H and S is that you're going to be calculating if this is true or not. Can H or S alone tell you if it's definitely thermodynamic or not? No, it cannot tell you if it is or not. But G can if they ask you to calculate delta G. So here is a reaction. I don't think y'all have the bottom part, do you? Do y'all have the big number at the bottom? No. Okay, so here's the deal. My first question is, what are all those lime green numbers? Okay, again, I can't stress to you enough how much the coefficients are going to happen here. So what is the standard free energy change for the following reaction? My second question is, where did this number, this number, this number come from? Tables, very good. What compound is missing? Why is it missing? It's 0. Very good. So, and I do want you to write this down. So if you calculated that, this is the number you would come up with. And I don't know why that less than 0 is up there. I don't like that. But if I asked you the question of, is this reaction thermodynamically favorable or not, how would you respond? Yes. What if part B was, what is the value of K? Greater than 1, less than 1, or equal to 1? Very good. And those are the type of questions that are very free and easy points on the AP exam. Is they ask you to calculate K, or they ask you to calculate E, or they ask you to calculate G, and ask you about one of the other two, and all they want to know is the sign or greater than or less than. And all you do is use that sign and that number to tell you whether or not it's true or not. So it is thermodynamically favorable. Yes, sir. I mean, sorry. He had his hand raised too. Thought you did this. Okay, go ahead. Did you get your question answered? Okay, go ahead. The what? Benzene. Yes, I'm sorry. Yes. Yeah, because of the structure, and again, you'll learn this in organic, which is the devil. I always hate drawing organic structures because I'm terrible at them. Because that's not, I mean, I'm telling you, it's bad. Like, I can't even draw it symmetrically. It's a little better, but it's awkward and oblong. So every point, and what I mean by that is every single time a line connects, that is where a carbon is represented. Okay? And so every carbon has two carbons attached to it. And so what you have is, let me actually do it in a different color. Yeah, you're going to have two hydrogens coming off of it. So you'll have one here, 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 here. Well, remember, it's three-dimensional. So however you want to draw it, if you wanted to draw them like this, you could. It doesn't matter. Yeah, it's an aromatic compound. And like I said, I could spend a year talking about all that, which is not any fun. I'm telling you, you don't want to do it. All right, so I want you to calculate delta G for this reaction. Now here, real quick, my first question is about entropy. Is this becoming more disordered or less disordered? How do you know that this is less disordered? Very good. We've got 2 moles of a liquid and a mole of a gas to 2 moles of a liquid. So essentially what's being taken, like what's canceling each other out? The 2 liquids. So you're going from a gas to a nothing. So this has a what sign of delta S? Very good. So this is negative S. So my first question is this working towards what nature wants, or is it working against what nature wants? Against, but you also have to remember, and again, I'm throwing this to several slides back, even if it's becoming more ordered, if the reaction is very exothermic, can it still be spontaneous? Yes. So we don't know the delta H of this reaction. But if we did, we could calculate it. But we just want to calculate delta G. So go ahead and calculate delta G and see what you come up with. The what? It's a kilocalorie. You'll just use that unit. What's happening, though, specifically here? Like if you had to write the words of what was happening in this reaction. What, like words, not formulas. Perfect. That's what I wanted you to know, to make sure that you knew that was hydrogen peroxide being formed. I'm going to let you calculate it, and then I'm going to give you a common sense idea or common sense approach to this. So this is how you kind of sort of set it up. Now, do you have to have the top part? No, but you definitely need to have something like the middle part. Did anybody get an answer to this? Say it again. Oh, thank you. That is negative. I'm glad you told me that. If you wrote it down like that, you wouldn't get it right. So what is the final answer? $59. Anybody get? Okay. 59 point what? And it's kilocalorie. why not joules? Kilocalories per mole of reaction. Now, so let me ask you something. TF or not TF? Not TF. And let me give you a very, very common sense approach of if you just thought about it, duh, I know that it's positive. Because you told me in words that this reaction has water and oxygen reacting to form hydrogen peroxide. However, does that happen in nature? You don't see hydrogen peroxide just falling out of the air. So let me ask you this question. What is hydrogen peroxide kept in? Why? Light denatures it. So just sunlight will actually make the reverse process of this happen. So how much energy is required of nature to actually make the reverse happen? A lot. But if you want to try to force this to happen, think about how many kilocalories you're going to have to put in. 59,000 kilocalories. Now, here's a trick question. How many of you remember how many joules are in a calorie? So, I actually want to do this, and I do want you to write this down, please. So, we had 59.0 kilocalories. So, the first thing I need to do is I need to get rid of kilocalories and get it into calories. So, what do? So, in 1 kilocalorie, I have 1,000 calories. Now, this is the next part that you need to know. So, in calories, we need to know joules. Does anyone remember that conversion factor? Very good. In 1 calorie, there's 4.18 joules. Now, will you do that calculation for me real quick? Or somebody. I just need a number. 59 times 1,000 times 4.18. 246,000 and what? I'm thinking in my brain. So, in essence, we need 247 kilojoules, which is a lot to make this happen. But if the reverse process happens, that's how much energy that nature is going to save. And it's going to do everything that it can not to burn all that, to force all that to happen. Does that make sense? So we cool with that? Now, again, the reason I showed you this is for this factor. I don't think they'll ever ask you to convert, but you never know with these people. They may ask you to. That's like the last part of the question to make sure you know calories and joules. Let me go back. Okay. Now, this is, remember whenever we had to take those reactions and flip them and change them and edit them and move them around? This is that type of reaction. This is your multiple types of reactions. So here's my question. We've got two different things happening. We've got diamond converting to carbon dioxide, and we've got graphite converting to carbon dioxide. And here's the crazy part. Are both of those delta G's positive or negative? They're both negative, which means both of these reactions are spontaneous or non-spontaneous. So diamond and graphite they're both negative, so they're both spontaneous. Okay, so diamond and graphite will naturally, in millions of years, turn into what? Carbon dioxide. Eventually, in millions of years, that will occur. Now, the time part is the kinetics aspect of it. But here's the deal. We want to know how much energy is required to go from diamond to graphite. So here's the deal. I've got graphite as a reactant. I've got diamond as a reactant. Are either one of these two, does it have diamond as a reactant? Which one? The top one. So do you agree that that one's locked into place? Okay. Now, I also want graphite as a product. Well, does either one of these have graphite as a product? So what do I have to do? I've got to flip this entire reaction. Now, mentally, can you tell me what happens when you flip it? What happens? Oxygen cancels and CO2 cancels, right? Now, if you flip the reaction in delta G's and H's, what do you do to the delta G or H? You flip the sign. And I'm going to ask you this because I need you to know this. If this were equilibrium and you flip the reaction, what would you do to the K? Take the reciprocal of it. I know every year that that's where students mess up, but you got to remember, can K ever be 0 or less? No. So that should be the biggest indicator that you can't have. So what is the answer to our delta G? So what is happening in our reaction? Diamond is going to, is it a positive or negative delta G? So is it thermodynamically favorable or not? It is. So over millions of years, diamond will eventually turn into what? Graphite. And vice versa. Now, how much energy would it take for diamond to do this? What if I wanted to go C diamond to CO2? Actually, as a matter of fact, it would have to be, well, it'd have to be plus O2 right here. How much what would we have to do there? Never mind, I'm being stupid. That's a dumb question. I was trying to figure out how to add them up, but that won't work. Now, real quick, and this I'm going to end here, but I want to talk about two things. Number one, people always ask me what is the different structural differences between diamond and graphite. Look at diamond down here at the bottom. Notice what we have. We have bonds. We have these covalent network structures. But look at graphite. What are these dashed lines? They're intermolecular forces. And what's stronger, a force or a bond? A bond, so that's why graphite. Now, one last little thing. This is completely off of this, but same kind of idea. Have you ever heard of graphene? Okay, if you haven't, you need to look it up. It's pretty cool. It's one of the new things in medical science they're trying to get for like skin grafts and tubes like heart casts. It's a 1 atom layer thick of carbon. And it's extremely strong and extremely durable. And they're trying to figure out different ways they can use graphene to do all these medical advancements in science because of what all it can protect, because things can't get through it.